In today's video, we'll learn about the laws of motion. When we think about the laws of motion, we usually think about Newton's three laws. What we're trying to measure when we're dealing with the laws of motion is force. Force is a push or a pull on some object. Force is measured in newtons, and 1 newton is equivalent to 1 kilogram times meters per second squared. In Newton's first law, an object moves with a velocity that is constant in magnitude and direction unless acted on by a non-zero net force. So this means that an object in motion will stay in motion unless acted on by an outside force. Our net force is a vector sum of all external forces exerted on the object. When we say an object has inertia, we mean that the object has a tendency to continue in its original state of motion. And the mass of an object is measured by the object's resistance to change in its motion due to a force. This brings us to Newton's second law. The acceleration of an object is directly proportional to the new force acting on it and inversely proportional to its mass. From this second law, Newton was able to derive the equation where the sum of our forces is equal to our mass times our acceleration. Newton came up with the law of universal gravitation, which states that every particle in the universe attracts every other particle with a force that is directly proportional to the product of the masses of the particles and inversely proportional to the square of the distance between them. This is seen below, where we have the force of gravity is equal to our gravity constant times our mass 1 times our mass 2 over our radius squared. And we see that the constant for capital G is 6.67 times 10 to the negative 11th. Finally, Newton's third law states if object 1 and object 2 interact, the force exerted by object 1 on object 2 is equal in magnitude but opposite in direction to the force object 2 on object 1. This can be summarized as for every action there is an equal and opposite reaction. To the figure to the right, we see this simply illustrated. As the man pushes off from the boat to reach the dock, the man moves forward, but the boat moves in an opposite direction. If we look at our first example, we have an automobile engine that has a weight whose magnitude is equal to 3,150 newtons. The engine is being positioned above an engine compartment. To position the engine, a worker is using a rope. We're asked to find the tension in the supporting cable and the tension in the positioning rope. So we can see this illustrated in the figure to the right. First, it's important to try to sum up your forces in the x direction and then sum up your forces in the y direction. So if we sum up our forces in the x direction, if we look at the tension in our supporting cable, we see that we have an x component that is going in the negative x direction, which is opposite of our angle. So our tension for the supporting cable will be our tension times sine of 10 degrees, which will be a negative since we're going in the negative x direction. And if we then look at the tension in our positioning rope, we see we have an x component, which we can see acting in the positive x direction if we make a right triangle below. And we'll see that our side acting in the positive x direction is opposite of our angle to our hypotenuse, so opposite over our hypotenuse. So since it's acting in a positive direction, we'll have the tension of rope 2 times sine of 80 degrees. And then since we're in equilibrium, we're equal to 0. Now if we sum up our forces in the y direction, we'll see for the tension in our first rope, we'll see our tension in T1 in the y direction is in a positive direction and is adjacent to our angle. So T1 times cosine our angle of 10 degrees. Now we have to find the y component in the tension of rope 2, which we'll see is acting in a negative y direction, but is also adjacent to the angle. So T2 will have minus T2 cosine our angle of 80 degrees. Plus we have the weight acting in a downwards motion in the negative y direction, So we'll also have minus the weight. And since we're in equilibrium, our sum of our forces in the y direction will be equal to 0 as well. Since we're trying to solve for the tension in rope 1 and the tension in rope 2, we can use the equation we formed for our force in the x direction to solve for one of our variables. So if we write our equation again, we have negative T1 times sine of 10 degrees plus tension in rope 2 sine 80 degrees is equal to 0. If we add T1 sine 10 degrees to the other side, we'll be left with the equation of T2 times sine of 80 is equal to T1 times sine of 10 degrees. We can get T1 by itself by dividing both sides by sine of 10 degrees. And when we do so, we'll see that T1 is equal to 5.67 times T2. So now that we have a value for T1, we can plug T1 into our equation for the sum of our forces in the y direction. If we do so, we'll see that if we plug our value of 5.67 times T2 in for T1 in our equation for the sum of our forces in the y direction, we'll have 5.67 T2 times the cosine of 10 degrees minus T2 times cosine of 80 degrees minus the weight, which we're given, of 3,150 newtons is equal to 0. Now if we add 3,150 to both sides, we can simplify our equation a little bit more to where we'll have our equation. Now that we only have one variable, that being T2, we can solve for T2. If we divide this side by 5.67 T2 cosine 10 minus the cosine of 80, our values will cancel out, which will only leave T2 on the left, which will be equal to 3,150 all over 5.67 cosine of 10 minus the cosine of 80 degrees. And when we divide this out, we'll see that T2 is equal to 582 newtons. Now since we know the value of T2, we can plug T2 back into our equation for the sum of our forces in the x direction, and we can solve for T1 now. So the sum of our forces in the x direction was negative T1 times the sine of 10 degrees plus T2, the sine of 80 degrees, was equal to 0. And now we can plug in our value for T2 to solve for T1. We have negative T1 times the sine of 10 degrees plus 582 for T2 times sine of 80 degrees is equal to 0. If we add T1 times sine of 10 to both sides, we'll have T1 times sine of 10 is equal to 582 sine of 80. Now if we divide both sides by sine of 10 degrees, we'll get T1 by itself, and we can calculate the value of T1 to be 3,300 newtons. In our second problem, we're asked a car of an unknown mass is on an icy driveway and inclined at an angle of 20 degrees. Determine the acceleration of the car, assuming the incline is frictionless. And then in part B it says if the length of the driveway is 25 meters and the car starts from rest at the top, how long does it take to travel to the bottom? And then in part C, what is the car speed at the bottom? First we're going to want to draw a free body diagram. In our free body diagram, if we represent this block as our car and our angle is 20 degrees at the bottom of our right triangle, the angle we see here will also be 20 degrees. And so since the car is acting in the x direction, we're going to sum up our forces in the x direction. And the forces we have in the x direction, in the positive x direction, which is going to be to the left in this case, will be mg sine of our theta. And then since our incline is frictionless, we don't have to worry about the force going in the opposite direction. And we know that force is also equal to mass times acceleration in the x direction. So we can simplify our equation into this below. And then since we're trying to solve for acceleration, we can divide each side by m to get acceleration by itself. And we do so, we'll end up with the final equation of g times sine times theta. And now if we plug in our values for our acceleration, we'll see we'll have 9.8 times sine of 20 degrees, which will give us an acceleration in the x direction of 3.35 meters per second squared. In part B, we're asked to solve for the time it takes for the car to travel to the bottom. It says the car starts from rest, so we know the car has an initial velocity of 0 meters per second, and the length of the driveway is 25 meters. And we're trying to solve for time. So we can use the equation of where delta x is equal to our initial velocity times time plus 1/2 our acceleration in the x direction times t squared. Since our initial velocity is 0, this part of our equation will be equal to 0. And so we have our displacement. We solved for the acceleration in the x direction in part A. And so the only variable that we can solve for is t. So if we rearrange the equation to solve for t, we see that t is equal to our displacement over 1/2 our acceleration in the x direction taken to the square root. So now we can plug in our values for our displacement of 25 meters times 1/2 our acceleration of 3.35 taken to the square root. And when we take this to the square root, we'll see that our time for the car to travel to the bottom of the driveway will be 3.86 seconds. And finally, in part C, we're asked what is the car's speed at the bottom? Or in other words, what's the car's final velocity? So the equation we have to solve for final velocity is our final velocity is equal to our initial velocity plus our acceleration times time. We have the values for our initial velocity of the car, which is 0, plus our acceleration of the car, which was 3.35 meters per second squared, times our time of 3.86 seconds. And when we multiply 3.35 times 3.86, we'll get a final velocity of 12.9 meters per second as our final velocity.